Hi everybody, we are back once again talking about the autocorrelated error problem in a simple OLS time series regression framework. Last time we talked about how to run some basic tests in Stata for the presence of that autocorrelated error problem I should say. Now we're going to look at, again, some pretty basic methodologies of having to solve that problem again in Stata. So what we're going to look at here are three solutions that are going to get us where we need to go. We'll look at how to create this first difference transformation, how to evaluate the output in Stata, upping the sophistication a little bit, looking at the generalized difference or generalized least squares estimation, and then lastly the Newey-West robust standard error option. Okay, so why don't we jump over to Stata. So we're going to pick up pretty much where we left off last time, where we're going to bring in some monthly time series macro data just for example purposes here. So from the Federal Reserve Economic Database, we're going to go grab the unemployment rate and the industrial production index. And one thing that we noticed last time, if we browse the data, right, is that we had one variable here, industrial production, coming in all the way back to 1919. Unemployment rate doesn't enter the data set until 1948, so we have all these missing observations here. One other way to deal with that, just for fun here, is that we can just get rid of that entire portion of the sample, right, and just keep the time periods over which all of our variables are represented in our data set. So we can just, in Stata, use this command drop if our variable who has missing observations, unrate in this case, is missing, equals dot. Right? So we'll get rid of those 348 missing observations, do a quick browse operation. Now everything starts at that 1948 point. We saw a different way of dealing with that last time. This is probably an easier way if we know we're not going to need any of those observations. The other thing we have to do before we get started here is to generate a time or a trend variable, and then indicate to Stata that that's how our data is organized here. So our command here will generate a new variable, just call it time or trend or whatever you want to call it, equal to underscore in, and then ts set time, and now browse the data again, and that'll be equal to 1 in our first period, and so on down the line. And if you recall the regression that we were basing our example on, again, just a very simple static model of unemployment rate at time t as a function of industrial production at time t. And again, we're not indicating this is a properly specified model at all, just for exposition purposes. And from that, we're not going to go through the whole testing procedure again, obviously, but we can just take a quick look at the residuals from this regression. Once it gets estimated, there it is. And if you recall, if we did that little eyeball test, if you will, for autocorrelation, bring up the time series plot, we saw very obvious indicators of that clustering pattern of these residuals, right? Lots of positive errors clustered together here, here, here. Lots of negative errors clustered together in this kind of sine wave cyclical pattern. And we established that as well with the AR1 t-statistic test and the Durbin-Watson test. So we can be pretty confident moving forward this regression does in fact suffer from autocorrelation, so we should be able to articulate why we care about that, right? So that means the variance, the standard error, the t-statistic, the p-value, the confidence intervals for all of our coefficients are going to be incorrectly calculated, invalid in a sense. So we want to be able to run this regression, but be able to conduct hypothesis tests. So we need to account for that autocorrelated error problem. So like we said, our first option is the so-called first difference transformation. So let's go back to the slides here to take a look at how that's going to work for us. So in the simplest case here, where we have a y variable as a function of x and our error term, and we're assuming now that our error term follows a specific form of autocorrelation, the AR1 process, right, where our current value is a linear function of its first lag, so that rho is the correlation between ut minus 1 and ut. And then this very important item added on here says that there is, underneath it all, a truly random, well-behaved error term. Call it our VT. And the important component for our purposes here is that the VT is not autocorrelated. So one way to think about a lot of these solution methodologies is we want to create a model where the error term is dominated by this VT component and not so much this problematic UT term. And that's exactly what this first difference transformation will do for us, right? So when we talk about a first difference or a delta YT, we're just talking about the change from one period to the next, right? So the difference between YT and YT minus 1, and then to make that into a regression model, right? Well, we just plug in our definition for YT here based on our prediction line there, and then we backdate everything on our regression line here to get our YT minus 1. So we have YT minus 1. Now we just collect up all the terms, right? The intercepts, the B0 here, the way we've written it out, that cancels out. We've got a B1 here times xt, a B1 xt minus 1. That'll collect into a delta xt. And then the whole point is we get this new error term that is differenced, the change from one period to the next. And what's going to make that useful is to remember that this UT is our AR1 process. So we plug that in here for UT. And now we've got a row UT minus 1 minus a UT minus 1 here. And that's going to collect up into this term rho minus 1 times UT minus 1. So the idea is, as rho, the correlation between lagged errors and current errors gets to 1, this term is going to go to 0, and the remaining error term is going to be exactly what we want, this well-behaved error term. So it's a little bit odd, right, that this procedure works best when the autocorrelation in the underlying model is most severe, as that rho term, that correlation, goes to 1. So in other words, sometimes this is going to work, sometimes it won't. But it's nice and easy, it's intuitive, it's a good first stop in your attempt to solve this problem. So let's see how it works in our particular case here. So there's a couple ways to generate differences in Stata. If you go back to Stata tutorial number 4 in this series, we look at some other examples of how to do that. We'll just kind of keep it straightforward here, and we're going to use simply the difference operator. We'll do it in the context of the regression equation, but just real quickly to get an idea of how this is going to work, we can generate a new variable, call it dun, which will be the difference, equal to d dot unrate. So that d dot is this difference operator, and if we browse our data here, well, we see what we've done here, right? We've got the unemployment rate here in observation 1 at 3.4, observation 2 is 3.8, so the difference between the two, what we just created, is the 0.4. From 3.8 to 4.0, it increases by 0.2. 4 to 3.9, it decreases by 0.1. So when you use that difference operator, have that little mental image of what we're creating, just the gaps between each observation here. And we're going to do that for our y and our x variable in the context of our regression command. And of course, what's going to come out of that is a new error term that is itself differenced, right? So all we have to do is use our standard regress command, but instead of unemployment rate as our y variable, it's d dot unrate. And instead of industrial production on the right-hand side, it's the delta x, the d dot industrial production. So here's our first difference regression model. One thing to note is that our coefficient makes a lot more sense here. We get a negative sign and a significant t-statistic on that coefficient, which means as industrial production goes up, unemployment goes down in differences, right? Notice in levels we had a somewhat surprising positive coefficient. So this already makes me feel a little bit better about this model. Of course, the important question for our context is, did it work? Are these error terms non-autocorrelated? So we can double check that real quick. We can simply apply the Durbin-Watson test, E stat d Watson. Remember, the closer that value of the d statistic is to 2, the closer rho is to 0. So the fact that it's a little bit above 2 tells us we have a little bit of negative autocorrelation. And we can verify that by predicting our residuals here. We already have a u hat from our original regression, so let's call this du hat from our differenced regression. And don't forget that comma r or comma resid. And as always, let's just do the visual here, take a quick look with that TS line. Now that looks more like a residual should look, right? Not really any visual evidence of clustering or positive autocorrelation. Looks like pretty random variation across 0, observation by observation, so we're pretty happy with that. And we can go ahead and run that AR1 equation, right? So just run today's value of, forgot the D, of that differenced residual as a function of the 1 period lag. And here we get a rho hat for this differenced error term of negative 0.06. It is in fact significant at 10%, so it looks like we have some degree of problematic negative autocorrelation in this case, which is better for a few reasons, mostly because it's much less severe here. So it's helpful. We didn't quite completely eliminate the autocorrelation problem, but we'd be much happier with this regression than the static OLS that suffered from autocorrelation. But you can easily imagine a case where we try to do this first difference model and it doesn't actually work for us, so we want to have a couple options available to us. So recall, option number 2, going back to our slides here, is that so-called GLS, or Generalized Difference Transformation. And the starting point is exactly the same, right, where we have our simple yt as a function of xt, but the error term follows an AR1 autocorrelation function. But the saving grace, right, is that we're assuming we have this well-behaved error term here. So remember, the big difference between the first difference approach and the generalized difference approach is that the first difference approach sometimes works, right? It depends on the value of rho, the degree to which you have success. Whereas the generalized difference model, as long as we get our assumptions right about the behavior of the error term, it will eliminate the UT error regardless of the value of rho. It's just basically designed from the ground up algebraically to do exactly that, right? So remember, the trick is, instead of generating our yt minus 1, or a delta yt, we insert the rho term here. So what's really going to play the role of our new dependent variable, taking over for yt, it's, call it this yt star, the current value minus some fraction rho times the lagged value. And the easiest way to see how this is going to work is just apply that just like we did in the first difference. So here's our yt minus rho, yt minus 1. Then we just do the algebra and things are going to work out. So we get a new augmented intercept term, this b0 times 1 minus rho. We get our b1, and then we collect up our x term, so it's xt minus rho, xt minus 1, so that's our xt star. And then, again, here's where all the action is. The whole point is to get this form of our error term. And we'll do exactly what we did last time, is we're going to say, aha, ut is going to be this assumed AR1 process. So we make that substitution, and here's the beauty of it. We've got a rho ut minus 1 minus a rho ut minus 1, and the only component of the error term that's left standing is the vt. Okay? So again, there's a lot of baggage that comes along with this mathematically to get to that vt term, but that's the whole point of this generalized least squares. Do what we have to do to get the well-behaved error that we want. So we can't really do this, quote-unquote, by hand in Stata, because we don't know the value of rho to use. So that's where this gets a little bit complicated, is we need to simultaneously get estimates of our B0 and our B1 and our B2 hat. Sorry. Excuse me. And our row hat. So that's what this so-called Cochran-Orcutt Price-Winston methodology comes in. So we are going to use the command here, PRAIS. So that's this Price-Winston estimation strategy, and we're going to have our Y variable, right, unrate, as a function of INPRO. So as far as the coding is concerned, that PRAIS, that Price command replaces regress, right? And we're going to use the option here, CORC, this Cochran-Orcutt procedure, and it's really just telling Stata to do exactly what we just said, is to go back and forth, estimate a row hat, use that to estimate the beta hats, use those to get a new row hat, back and forth, back and forth, back and forth, until we get convergence, right? And that's what's happening here. So these iterations, iteration 1 through iteration 26, these are choosing different values of rho to get different values of beta and bouncing back and forth. And we finally converge here at a value of rho, and look at that, it's at 0.9984. So that tells us this is going to look a lot like the first difference transformation, right? When rho is equal to 1, these are going to collapse to the same thing. And look at this, we have a Durbin-Watson statistic from our new model here, virtually identical to what we had with the first difference. That's not always going to be the case, but as rho goes to 1, these are going to converge. And our coefficient here, virtually identical to what we saw in the first difference. So the nice thing about this command is it automatically gives you that evaluation. It says, okay, we're correct, we're going to attempt to correct for it, and we're also going to tell you how well we did. So we have that same result, a little bit over 2, so a little bit of negative autocorrelation. So in this case, either of these two options would be perfectly acceptable, again, if we had some confidence in the underlying model. Okay, so that leaves us with the last option, which in the case when the first difference, the generalized difference, don't seem to work, there might be a more complicated form of autocorrelation. It doesn't follow an AR1. It's not quite eliminating the problem for you. We've always got that robust standard error option in our back pocket, right? So let's remind ourselves again what that's going to do for us. So remember, we've seen the robust standard error option in the context of heteroscedasticity, the white robust standard error, right, which looks something like this. And the main point there is that we have a, sorry, lost my pen here. There we go. That we have this period by period estimated error variance, that we're not assuming a constant error variance. We have heteroscedasticity. So that's going to be our heteroscedasticity robust standard error, but we have to add a new element to it here, right? That when we have autocorrelation, we're going to use this Newey-West option, which starts with the white robust standard error. So we're still okay if we have a heteroscedastic error. We're not assuming homoscedasticity. But now we're also accounting for these pairwise covariances across error terms, right? So we're not going to get into it too much right here, but this can account for multiple lags, multiple orders of autocorrelation. Right? And, right, in the Gauss-Markov context, we assume these are 0, right? So this whole thing drops out. But now we're saying, wait a minute, we've been doing it wrong. We really should be allowing this term into our calculation. Right? So in the case of positive autocorrelation, right, this is going to be some positive number that we're going to be adding to our previous estimates of the variance and standard error. So our standard errors, our variances are going to go up, our t-stats are typically going to go down, but it's going to be our correct calculation, right? So that's what Stata is going to be doing for us behind the scenes. All we need to do is know how to call that up, right? So our command, right, we're going to leave the y and the x the same, so it's unemployment rate as a function of INPRO. And unlike the white robust, where we would use regress y, x, comma, robust, here we start off from the beginning calling up this robust standard error. So the actual estimation command here is Newey for the Newey-West robust standard error. And then we also need to tell Stata how many lags to account for. It's worth doing a little bit of trial and error, a little bit of testing for higher order autocorrelation, but if the bulk of our autocorrelation is in that first lag, kind of that first concentric circle there, we would do this lag 1 option, and what we'll see is our coefficient estimate here, our beta, is going to be identical to what we had with OLS. Let's actually go ahead and call that up, just so we can see it side by side here. So let's just regress our unemployment rate as a function of industrial production. So up here is the Newey-West robust option, here is the OLS option, and the point here is that we're not doing anything to the process of estimating the coefficient. That's going to be exactly identical. All we're doing is adjusting the calculation of the variance, so everything associated with that is going to be changing. And as we'd expect, we get a larger standard error, a smaller t-statistic. In this particular case, there is no additional cost associated with it. Right? The level of significance is really identical, so it seems to be a good option here, specification issues aside. So what you should be able to do at this point is, given a time series regression, be able to use a variety of tests to look for the presence of autocorrelation, and then a variety of correction schemes to account for the presence of autocorrelation when you find it. So if you have any questions on the topic, leave them in the comments down below, and I will see you guys next time. Thank you.